Good afternoon. I'm Professor Sever. Today we're going to discuss analytical techniques for evaluating limits in Calculus 1. First, we'll center our attention on basic properties of limits. Now, we should recall that we've already discussed epsilon delta definition of the limit, so today we're going to be looking at theorems, not the definition. So we'll actually start to begin to develop the theory that we will use to evaluate limits, not using the definition. If I were to prove these theorems, I would of course use the epsilon delta definition in its general form to prove each of these statements. First, let's recall that the epsilon delta definition of the limit involves the deleted neighborhood around C. In other words, the definition of the limit doesn't capture what happens to the function f at C, only what happens to the function f nearby C in that delta neighborhood around C. In some cases, we will see that the limit as x approaches C of f of x is f of C. In other words, the limiting value matches the functional value, and in these cases we would say that f is continuous at C. And we'll discuss this in depth in a subsequent section. But we will see the initial theorems in fact have this property. So let's take a look at some of the first basic limits. What is the limit of a constant function? So suppose f of x is equal to b, as we see here in part 1 of the first theorem. Well, the limit of the constant function at any value of c is that constant value. And we see this illustrated in our first example. The limit as x approaches 2 of the constant function 3 is of course 3. And if we look at this graphically, I think that would be easy to see, of course. How would we prove this in general? Again, we would use the epsilon delta definition or technique. The next theorem, basic theorem, is what is the limit of simply the identity function f of x equal x. As x approaches c of x, the answer is achieved again by the functional evaluation that we just discussed. It's just c. Notice this is what you would get if you plugged in c to x. So this is a theorem which again can be proven. So we see this illustration in part b. The limit as x approaches negative 4 of x is simply negative 4. Again, we see this being accomplished through functional evaluation. You just plug the negative 4 into x. Part 3, a simple polynomial. Now x has to be a positive integer here, so notice x is not negative 1, which would really be the reciprocal 1 over x function. That's coming later in today's lecture. But simply if x approaches c of x to the n, the answer to this limit, the limiting value, is c to the n. And again, we perceive this as functional evaluation. Notice here in this part c, I'm plugging in 2 to the squaring function. 2 squared is 4. That's the limiting value. So the first 3 of our basic limits could be achieved by functional evaluation, which is an example of what these comments are here. Okay, now these are some technical properties. These are great properties to have. Suppose you knew that the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is k. Okay, now one thing to note, we have two different functions, but we have the same c value here. They're both considering the same c value. In other words, the limits are approaching the same value of c. So what we're saying is the limit as x approaches c of f of x exists and it's L. The limit as x approaches c of g of x exists and it's k. Well, in this case, this really says f and g are nicely behaved at c, or nearby c really. And what we get is the 5 following nice theorems. 1, the scalar multiple. So the limit as x approaches c of a constant multiple, b of f of x, is of course going to be b times L. And if you add the two functions together, f plus g, then the limit as x goes to c of that sum or difference is just the sum or difference of the two limits. So if we look at this, the additive version rather of this theorem, what this says is, in linear algebraic terms, is that it's a linear operator. So in other words, the limit of the sum is the sum of the limits, provided both limits exist, and that's keenly important to take note of. The product is the same way. The limit of the product of f times g is the product of the two limits. Notice, or let's recall, that L is the limit of f as x approaches c, and k is the limit of g as x approaches c. Same for the quotients. The limit of the quotient is the quotient of the two limits, provided, of course, that the denominator is not 0. Now, this theorem doesn't speak to what happens if the denominator is 0. It just says that if the limit as x goes to c of f is L, if the limit as x goes to c of g is k, then we can find the limit of the quotient in those instances where k is not 0. So again, quotients are well behaved, products are well behaved, sums or differences of functions are well behaved, and of course the scalar multiple is also well behaved for limits. Finally, if n is an integer positive, which means it's a natural number, we can get another nice theorem of exponentiation. The limit as x goes to c of f of x raised to the n is just L to the n. So these are very nice, simple, technical limits that are actually used to prove some of the subsequent theorems. In other words, we would develop these theorems so that we don't have to prove more general theorems using the epsilon delta definition. We could rely on these theorems and perhaps mathematical induction, for example, to show the limit of a polynomial is obtained by functional evaluation. Now let's look at this example. How would we do this example using our prior theorems? Well, first, let's see. Let's look at this function 4x squared plus 3. Now eventually we'll have a different theorem, a little higher level, to evaluate this in one fell swoop. But right now, how can we evaluate this with our previous 5 results? Well, notice we have a sum right here. We have a scalar multiple, and we have the squaring function. Okay, so let's see how that would work. The limit of the sum is the sum of the limit. So the first thing we could do is separate this one limit of the sum of two functions as the sum of two limits. It looks like the limit is being distributed. That's really not the right term. It looks that way, but you're separating the limit in terms of the two constituent functions comprising this sum. Okay, so now this one we know. We can just kind of skip ahead a little bit. What is the limit as x approaches 2 of 3? Well, that's just 3. We see that. That's an example of this theorem. Now, this piece. The scalar multiple we can pull outside of the limit. As x approaches 2, 4 isn't going anywhere. 4 is constant. That's really what this theorem is saying. We could rewrite this as, what is L? L is the limit as x approaches c of f of x. So this is really b times the limit as x approaches c of f of x, and if we think about it, it looks like the b can be pulled outside of the limit, and in fact that's the way we envision handling scalar multiples. And now the question becomes, how do we handle this here? This can be evaluated using this one, number 3, where n is 2. Just as we did here. So again, on this example, we used 3 separate theorems to evaluate the sum of these two functions. And finally, 2 squared from this piece is 4. 4 times 4 is 16. 16 plus 3 is 19. You should note that at each stage, you need to write the limit until you're evaluating the limit. Here, the limit is being evaluated from this step to this step. Now I could have evaluated the limit here. I left it so that you could see as the observer that it's between this step and this step where I'm now applying the theorems to evaluate the limit via functional evaluation. Namely, I'm plugging in. I plug in the 2 to the x squared to achieve the 4, or 2 squared, which is 4, and then I plug in the 2 to the constant function 3, yielding 3. Again, you might say, well, how come I can't just plug in on the first step? Of course you can, but in terms of this presentation, I haven't developed that theorem yet. That theorem will be coming in a few moments. As we saw in the previous example, the limit as x approaches 2 of the polynomial function is simply the functional value of p at 2. So let's see that here. Notice I did it in pieces, but as I just said, we'll have a theorem which says I can just plug in, And that's what this statement wants us to observe at this time. Notice that 19 that we had is, in fact, what I would have obtained had I plugged in the 2 to p. P of 2 is, in fact, 19. Let's see what this says. This function valuation property is valid for all polynomial functions. Of course, that statement would have to be proven. We will see that it is also valid for rational functions with non-zero denominators and many other functions as well. And remember, what a rational function that has a non-zero denominator at a particular value says that that value of c is in the domain. And again, we have a remark here that actually what we're doing is we're building to this notion of continuity, which you may have already read by the time that you're seeing this video or reviewing it on a subsequent viewing.